Also, we're recording this to distribute to the folks who attended our RCR program but could not attend today. So are you ready to go following my introduction?
Yes, I am.
Great. Okay. Well, probably many of you know Dr. Oswald Steward. He's a distinguished professor in anatomy and neurobiology. He's also the founding director of the Reeve Irvine Research Center, which has a very heavy emphasis on spinal cord injury research. He's served as the senior associate dean for research within the School of Medicine. And also, what I think is very impressive is that Oz was elected as the president of the Society for Neuroscience. And for those of you in the field of neuroscience, you know that that really is the largest meeting in the world in that particular field. The other thing that I think is really quite impressive, especially for our group, is that Oz won this the so-called Landis Award for outstanding mentorship from NIH. I thought that was very, very impressive to see.
Thank you.
His areas of scientific expertise are very broad within the field of neuroscience, but with a specific applications to mechanisms of synaptic plasticity and neural repair and spinal cord regeneration. And the other thing that I want to note is that Oz, and Oz, you can correct me on this, but the award that you received from NIH with regards to rigor and reproducibility, was that in 2013-ish?
I think it was 10.
Okay. Yeah. Yeah. And so that really was at the forefront of trying to get at issues related to rigor and reproducibility. And Oz led a group that specifically focused in on critical issues related to enhancing rigor and reproducibility within the field of spinal cord injury. And so, Oz, thank you for taking time out of your schedule as always, and look forward to a fantastic presentation. Thank you.
Well, thank you. Thank you, Vince. Really appreciate it. And that was a lovely introduction. Okay, so basically, what I'll be talking about today is scientific rigor in biomedical research and focusing primarily on really data collection and analysis. There's all kinds of ways that people think about rigor, but fundamentally, the start of everything is when you sit down to plan your experiment and when you actually execute your experiment. And as I'll sort of lead into here, one of the things that we discovered in our replication experiments was that many of the issues pertain to to the actual execution, but also the reporting of data. So you'll see kind of what I mean by that. I'm assuming that since this is ICTS, most of you do human subjects research. Is that a safe assumption? Please somebody chime up if that's not the case.
It really goes across the entire spectrum, though, from animal on up to
okay,
humans.
So there are some animal folks here?
Yeah.
Okay. Yeah. All right. So good. So let's just jump right in. So basically, where did all this start? It actually started back in 2005, or even earlier, when there were multiple reports from different fields indicating that published findings can't be replicated. And this wasn't the worst findings. This wasn't bad papers. These were good papers that were published in high quality journals. And several different, I guess, really areas of focus tried to actually bite into this and figure out what was going on. The cancer field was one of the earliest. And they funded high-profile replication attempts to actually reproduce papers that were driving clinical trials and considered to be very important. And in fact, what happened is that many of those papers failed to replicate. And so that triggered a real concern and has led to a whole series of things that I'll tell you about. But just to jump ahead, NIH has modified its requirements for proposals. It's really modified its requirements for training in scientific rigor and training grants. And fundamentally, journals have really changed their requirements and review practices in a very fundamental way. And basically, what was okay a few years ago is not okay today. And unfortunately, I think a lot of the senior investigators in all of our fields have sort of failed to catch up. So you people who are coming up are the ones who are going to be leading the charge on this, and perhaps sometimes sometimes you might have to drag your PIs along with you as you go because um, we are sort of set in our ways. Okay, so this is just a series of examples. If you're interested in reading some of the background here of the papers that began to identify the problems. They will, as you see, have been they've been published now almost 10 years ago. So it's not a new problem. Um, this is just again some data for you. Basically, again, that a large percentage of studies don't replicate. The problem turns out to be statistical analyses and also really the way things are reported partially up until I'll say about 10 years ago, partial reporting. These are estimates that emphasize the problem. That something like $28 billion a year in preclinical research funding is spent on things that don't reproduce. And these articles have now been really widely covered in the general press. And obviously, these things come to the attention of Congress. The impact of that attention varies, depending on the administration, of course. But I think that it is reasonable to propose that one of the reasons that there is a loss of public trust in science is that there is realization that science isn't perfect and that we really have to kind of correct ourselves. So, NIH, NSF, National Academy, scientific societies have acknowledged the problem. They've been trying to address it now for about a decade, and really it's going to involve everybody. So here we are. And that's what I'm going to really be focusing on today, what we in the trenches need to do, can do. Just to sort of define some terms. Replicability, what is that? Well, it's really the ability to duplicate, that is, repeat a prior result using the same source materials, really the same everything. And just to start out, that term really should only be used for results of a specific experiment rather than an entire study. So when I say things fail to replicate and all those data that I showed you earlier on, it really refers to specific studies. The entire study may have pieces of it that are okay, but others that is other pieces that are not. Reproducibility is probably a more useful term, which is the ability to achieve similar or identical results using roughly comparable materials. May or may not be identical. Maybe the antibody is different. Maybe the drug is slightly different. Maybe it's a new batch. And this is really referring to when findings from a study are obtained by independent researchers doing things slightly differently, but really bolstering the concepts that were found in the original study. Generalizability is ability to apply a result broadly across settings, systems, conditions. Again, maybe different animals, whatever, or different animals that are even not invertebrates to vertebrates, something like that, where a fundamental biological principle is discovered and then applied to a system that is more close to human beings. Translatability is special, and that's a very different issue. That is the ability to apply research discoveries from experimental models of all different types, ranging from animals to cell cultures to organoids of cells, whatever, to really human health. And that's a big one. That's a huge barrier that has a lot of issues going beyond the basic scientific rigor. And I'm sure that you've heard from others about that. Okay, I just used the term rigor. What does that mean? That means the use of unbiased and stringent methodologies to analyze, interpret, and report experimental findings. And the final term, which is really important, is transparency. And that is really reporting experimental methods and materials in a way that allows others to replicate it. This was the thing that was really fundamentally missing when I sort of got into this uh, now 15 years ago. The method sections of journals back then were incredibly brief, maybe 10 lines. We did this just like we did before, and, referencing a bunch of papers. And the problem is that, in fact, when you went back and carefully looked, when you went and asked the authors, what did you really do? It turns out they didn't do things exactly the same way. There were fundamental differences. And so now, most of you may know that the major journals now insist on extremely detailed methods, and that's a good thing. And there's no reason not to do it. In the old days, method sections were short because these were printed on paper. Paper pages cost money. But now that almost everything is electronic, there's really no reason not to have thorough and complete and transparent methods. Okay, so basically, sort of, how did I get into this? I guess it was 2000 and actually 2003 that this first started, Vince. I think I said 2010. So uh, we got started in this because the National Institute of Neurological Disorders and Stroke uh, really realized that something needed to be done fundamentally. And so they funded contracts. And the contracts were actually to select and replicate promising studies. In our case, it's spinal cord injury. And actually, it was the only case that was funded by NIH. We applied at UCI, the Reeve Irvine Research Center, Miami project at University of Miami, and the Ohio State University were also funded. Over 10 years, we replicated or tried to replicate 20 promising studies. These were not, again, these are not bad studies. We had a group of people, an outside committee that said, okay, these are the best studies this year that came out in the field of spinal cord injury. Let's try to replicate them. So this was not trying to fail, it was actually trying to succeed. And the results of 18 replication studies were published. Now you might say 20 years, 18, I'm sorry, 10 years, 18 studies. How can that be? It took a long time to replicate these. Actually, these are spinal cord injury studies, most of which take months to do. You might do an animal model, you might create a spinal cord injury, and most of these studies involve assessment of regeneration and recovery of function. Again, months of work go into each of these. So that's the reason there were only 18. The two that were not published were not published, not because they're very much different, but for technical reasons. We realized at the end of those studies that they really didn't, they were not able to actually meet what we felt were the criteria for sharing with the field. What was the outcome? About 10% of the published results were replicated. And again, remember that this means experiments, not the entire study. So there were studies where some things worked, some things were replicated, but fundamentally 10% of the results replicated. So really the impact of those studies was totally minimized, I guess. We published an interim report in 2012 that really just described kind of where we were on those studies at that time, and that's cited there. Okay, so why? What was wrong? Well, I've already mentioned this, but the problem partially was that the method sections of the original papers were incredibly sparse in detail. And that was the journal practice. That's what people did. But it was also misleading. What do I mean? When you do a spinal cord injury study, or really any study involving an animal model of a disease or disorder or injury, you have different groups. And in a spinal cord injury study, you might have 3 groups, and maybe there are 15 animals per group. That's 45 animals. There's very few labs that can actually do a spinal cord injury experiment all at once. Instead, what happens is that you do a few animals here, a few animals there. And what was happening was that people were doing these studies sometimes over years and putting the groups together. And then when they reported them, it was as if they did the experiment at the same time. the details on how those groups were actually formulated and put together were totally absent from the original papers. We did 3 groups with 15 animals each, and here are the results. So when you go back and try to replicate, it's impossible. When you talk to the original authors and they say, we did this over 3 years, 3 animals at a time, sometimes, they didn't even kind of have good records on how the groups had been formulated. It was impossible to replicate. I'm going to come back to that. The other thing, details of the procedures and methods were not available, even when you contacted the original authors, because back a decade ago or more, the record keeping in many labs was not up to par. This has changed dramatically, and actually there are now record keeping and preservation requirements by NIH. And I'll come back to that in a bit. Those of you who kind of monitor retractions of papers know that many papers are retracted because the authors can't find the original data. There's some question about a figure. What's wrong? This figure seems to be modified in some odd way. And to really credibly deal with that, it's required to go back and find the original images, the original data, and the data preservation in those days, at least in the animal work, was not good. So details. And so you really couldn't replicate the studies entirely. But even when most of the conditions were apparently duplicated, the key findings were not replicated. Now, the common response, of course, was, we didn't do it exactly the same way. Well, of course we didn't do it exactly the same way because we couldn't. But that was the most common criticism that we got from the authors that we replicated, most of which were, by the way, very cooperative. And, I thought when I started this project that there was a danger of making enemies. I made it through almost the entire thing without making any enemies, but not quite. Most of the authors were really quite, actually, I'm not sure glad is the right word, but it was a good exchange. It was a cooperative exchange, and everybody wanted to get it right. So that was really good. Okay, so what did we all conclude from this? And this was the consensus from us and from the original authors. Whatever was going on was not, any kind of misconduct. It was just that the conditions of these experiments were really critical. And even, when there are things that you think you're doing the same way, sometimes or most of the time it's actually no. So what that means is that the findings, they were what they were, but they were not robust across conditions. In other words, they're not generalizable or even reproducible, okay? Going back to our terms. And of course, the problem is that those of us who do spinal cord injury or other disease modeling want to be able to do something that is going to have an impact on the disease or disorder that we're investigating. So if the findings are not robust across, really minor conditions, it's certainly not something that could ever be translated. Again, lack of replication does not necessarily invalidate the original finding. And we've all kind of agreed that it really is just a biological thing. But of course, most of you might be saying, well, why didn't somebody just, do the experiment again and find out the conditions that are critical? And the question is, who's responsible for that, right? Is it the original authors? Is it the replicators? And who's going to fund it? NIH wants novelty, right? They want things that are going to have a big impact. And kind of digging down into the details is just not something that NIH is going to fund. And in fact, didn't fund. So a lot of these things have actually never been worked out in terms of what it was that was actually causing the differences in response. Okay, so what is, again, the sort of issue, biological variability, but flawed experimental design, or at least not quite rigorous experimental design, is part of the problem. And the other thing is that flawed analyses that are contributing to type 1 errors. I'm going to be talking a little bit more about the details of that. We, at least in the work that we did, there was no evidence ever of any scientific misconduct on the part of the original authors. But in other fields, there are differences of opinion regarding this. And again, I would point, if you are kind of interested in this, there's something called Retraction Watch, which is it's sort of a watchdog organization. But basically what they do is report kind of all the papers that are withdrawn and all the people that are accused of scientific misconduct. It's a little bit of a tattletale kind of thing. But it is useful to look at that and see why papers are getting retracted. And I'll just go back. A lot of times it's a very simple, honest mistake that there was some question in a figure, but the figure or the data were not preserved. You could not go back and prove that the data in the paper were actually reliable, and therefore the paper was withdrawn. It just is so incredible now to make sure that whatever you do is preserved in a way that it's going to be available both to you, because you're the ones who are going to be first authors on these papers, but also in the labs in which you're working, because you may leave and the lab may be the one that is responsible for preserving those data. And again, sometimes it's a matter of the lab being, the PI, being the one that fails, but you who have published a nice paper are forced to retract it. It's a very unfortunate situation. Now, having said that scientific misconduct is a small part, there are these other things. The one published one is there, but there's just one huge one that some of you may have heard of. This is the Maslia episode. So this was something that came out just a little over a year ago. This is Eliezer Maslia, who was a UCSD neuroscientist, Alzheimer's disease researcher, director of the National Institute of Aging. By the time this actually came out, and I think it was a ridiculous number of papers that were questioned, many of which have been withdrawn. So it isn't that there isn't scientific misconduct out there. And this is an evolving situation that we really don't quite know what the full outcome is going to be. Okay, but this kind of thing just causes huge, huge negative press for science. As you can imagine, well-deserved negative press, I might add. All right, I'm going to stop there. Doing this on Zoom is a little bit, I don't know, awkward, I guess, but I'm going to stop there just for a second, see if anybody has any questions. I'm not sure how many people we have in the audience. I guess I could go over here and look, can't I? Yeah. No questions?
I had a quick question, Steward. I was wondering, what is your opinion on method sections that reference other papers? Like they say, if you want to know how we did this part of the experiment, reference to this other paper that may have some of those more details. And the reason why I ask is because I find that maybe sometimes, to your point where you mentioned with that experiment where there were some slight differences, some slight nuances that were not detailed and they were missed. And when you go to replicate it, you need those nuances, you need those details. And sometimes in referencing another paper, there might be some small alterations that may have happened in the methodology that are kind of left out because it was, referenced to something else. So sometimes those papers are reference you to a paper which referenced you somewhere else. So now you're three factors removed. So I'm wondering what your thoughts are on that as far as spelling out everything you did in your paper or referencing other papers to look at their methodology.
I think and thank you for that question. That's a great question. I think what most of you are going to find is that these days, and I'll come back to this toward the end, these days, most journals have completely modified their practice and basically don't allow that anymore. They basically say, okay, you have to have all your details right here. The Cell journals are particularly, I think, structured about it. And I'll come to that at the end. They have a section in in all of their papers called STAR methods. And when you actually submit the paper, um, there are pages of detailed methods that were used, literally quite everything that was done in the experiment. I think, that my personal opinion is that's the way to do it. We go actually so far as to report the order in which we did surgeries on animals in the course of a day, because well, I'm this is when I'm doing this in person, I always ask people, okay, if you're going to have a surgery, right, what time of the day do you want to have the surgery? Is it early in the morning, your first surgery of the day, late in the day? And the answer is probably not the first surgery, but early, because, yeah, your surgeon, like all of us, needs to wake up, and so it's probably a little bit coffee deprived at the first one, but the second one, that's where they're on track, and then by the end of the day, I'm just saying, surgical skill, like everything else, varies by fatigue. So we literally list the order of surgeries in animals, and sometimes we get a comment back from the reviewers, oh, you don't need all this detail, and I say, yes, we do. And if what I've actually come to do is just insist that we're going to publish it, and we've won every one of those arguments that we've had. So thank you for the question. It's really, really, really important. I think
Oh, yeah, thank
going
you.
forward, that's going to be increasingly the norm, though. Other questions? Thanks for that one.
Later on, don't want to interrupt your train of thought here, but maybe we can also talk about the role of AI in terms of being used to detect scientific misconduct and other issues. So, but that would be a discussion at the end.
Yeah, no, I think that it's probably a good thing to talk about right now. Because everything that I'm going to be talking about from here on is sort of options for solutions. But Vince, you really raised a great point. These days, there are AI methods to track, to trace, whatever, um, identify AI generated text,
Yeah.
to identify text that is repeated from other publications, uh, uh, to identify errors, or rather modifications of images. So um, many of the good journals use these things routinely, and they'll find something, they'll send it back to the author. Hey, this is duplicating something that's been previously published. You can't say that. You can't do that. Um, which I'll just say, by the way, I have a little bit of trouble uh, kind of coming to grips with what that means for a method section. And going back to Joshua's question, if you have to present the methods in every paper, and it's the same methods that you're going to be using, in several papers, you are in fact repeating the text, and the AI programs will find it. So, I mean, for me, that's fine. It's methods. I'm doing the same thing. I'm going to say the same thing. Um, but just to say that is one of these things that how do you deal with that, right? Um, but the other thing to know is that there are what are called sleuths out there. And these are people who just enjoy finding things and bringing prominent people down. And, without kind of giving it away, they tend to go after Nobel laureates and things like that, or very prominent people. And if you want to find that, you can very definitely find it. For example, in Retraction Watch and other things. So, we it is no longer the case that, once you've got it in press, you're good. There are people out there who just love to find things that, again, um, that are wrong. So, and let me say, and maybe I could come back to that. There are things that people do quite innocently, and kind of don't think about what it might mean for these new programs. And I'll just say this in particular with regard to images. Um, you might have an image where there's an ugly piece of dirt, a microscopic image. And so you might say, that looks so ugly. I'm going to copy a piece of background. I'm going to paste it on there to cover up that dirt. Well, that's image manipulation. Now, it's actually okay if you explain in the figure legend, hey, there was a piece of dirt here that I covered up because it's ugly. It's called figure beautification. But the programs, the AA programs will absolutely find that. So
Yeah.
anyway, that's getting down into the weeds of things, but it's a really important issue. And thanks, Vince, for the question. Other questions? Okay, I'm not watching for hands come. I'm watching for hands come up, but I'm not sure I'm going to see them. So just speak out if you have any questions. By the way, interrupt me too. Normally, I'd love to be interrupted. I know it's a little bit more awkward on Zoom, but okay. So just again, kind of some terms. What is scientific misconduct? It's fabrication, falsification, plagiarism, and then those other terms that are kind of casually used is hoaxing, forging, trimming, and cooking. And I will say that I think, in my opinion, if you deliberately use something that's non-rigorous to deliberately conceal or misrepresent, then that's real close to scientific misconduct. But there's always a line. So scientific misconduct is like anything else in our society. You are investigated by a university committee, an anonymous university committee, and there's a finding of either guilty or not guilty. And I use that term in the same way that people do in the legal sense, meaning when you say not guilty, that doesn't mean innocent. It means not guilty, right? So it's very important to know the difference. All right, enough of that. And we did publish after our work a paper that talks about really some of the principles that can be used to improve practices, mainly for spinal cord, well, actually for preclinical work. And I published this together with Rita Bally's-Gordon, who was really a very prominent person in the biotech field. And she used to tell me, anything you do is preclinical. When I think of preclinical, it's, something different, but that was a useful lesson. So yeah, just completely gratuitous self-promotion here. If you want to reference this paper, feel free. I just boost my whatever. Okay. So here are some of the things that we identified as problems. And this is particularly true for animal research. Those of you who do clinical research or human subject research already define experiments, right? You put in an IRB, there's a listed number of people that you're going to recruit. When you're finished with that, recruiting that number, the experiment is over. That's not true of a lot of basic science. There's a lot of work needed in a basic science laboratory to just test things out, to do pilot experiments, to try things. And then you've got something, and so you finish the experiment. But what do you do with those data that you did on the way there, right? Most of the time in the past, and to some extent now, all those data tend to be wrapped together. I might do an experiment in spinal cord injury where I try a drug, and I'll try it on a few animals, and wow, what a great effect. I'm going to now, add more animals and do whatever. And then at the end of the day, so the point of that is when you do a pilot study, it's different than when you do the real study. So it's at least in my opinion, so important to say it. This is where I've stopped my preliminary studies, my pilot studies, whatever, and this is where I'm going to start the real experiment. And the corollary of that is the way I just explained it. So I might do a pilot study with, let's say, 3 animals per group. Looks really good. So I do more animals, and then I throw it all together. And I do a statistic, and oh, darn, it's not quite p less than 0.05. And oh, let's just add some more animals, right? That's called testing to a foregone conclusion. I'm assuming that I don't have enough animals, so I'm just going to add more and I'm going to get a significant result. I cannot tell you how many times I go to basic science labs and a student will say, hey, here's where we are. We're just going to add more animals. It's not quite statistically significant. But this is one of the things that, just happens. And it is even not, it's not even, I'm not going to say the word, it's not wrong, okay? But when that happens, it's so critically important to actually say it in the paper that this is what I did, right? That's where the big thing of transparency comes in, rather than just saying, oh, we did this experiment and this was the number of animals that we did it, and look what a beautiful result and statistically significant. That was what was wrong a decade ago. Okay, bias. Bias is a big deal. I'm going to show you what I mean by bias in a second. Lack of contemporaneous controls was another thing that we identified. So in human subjects research, you very often do one person or one patient at a time. That's the way it's done. So you don't really have a contemporaneous control. You don't have, one person standing here and one person standing here, and you say, okay, you drink solution A and you drink solution B. So with human subject research, I think there's more formalization of non-contemporaneous controls. But again, in animal studies, there's not really any reason not to have a contemporaneous control, but there is, at least in the studies that we replicated, the implication that there were contemporaneous controls. But in fact, what happened was that in many cases, people would do, the control study on one day, the experimental study on the next day. Day-to-day variability contributes. So this is one of the things that we think contributed to the lack of our ability to replicate, because we did, in fact, contemporaneous controls. Improper data exclusion. That's something that is always a question. So suppose you do an experiment and there's an outlier or 3 outliers. What do you do with those data? And those outliers totally mix up the statistics. Do you exclude them? There's good reason to think maybe so. There are some statistical tests that people can use that, 2 standard deviations away from the mean of whatever the group is, you could throw those data out. The problem is that a lot of times that's done post hoc because they didn't get statistical significance. And that's probably okay, or at least I think it's okay. If you say that, if you plan your experiment and say in advance, these are going to be the conditions under which I exclude data. In other words, a priori criteria for data exclusion. But if you're doing it post hoc because you didn't, because you're essentially seeing data that you didn't make it and you're going to, work the data until it is statistically significant, that's where problems come in. Improper statistics, there's long lectures that can be given about that. In our case, one of the things in spinal cord injury, but also in a lot of basic biology, we found, and you'll still see papers where you'll see a graph with 5 bars, let's say 5 bars, and the comparisons will be by a t-test. That's totally inappropriate because you're doing multiple t-tests, and that increases the probability of a type 1 error, okay? Guaranteed, if there are more than 2 bars on a graph, the analysis should be by ANOVA. As you're reading papers, you might just look at that and amuse yourself how many times a t-test is still showing up. It is possible to compare 2 groups, but only statistically speaking, after you've run an ANOVA, there's an overall significance by the ANOVA. Then you could do post hoc comparisons that actually account for multiple comparisons. Bonferroni corrections, those are called. Talk to your statistician. P-hacking, what is that? Well, that is basically the what I sort of have already alluded to. You do a statistic, you don't have statistical significance. It's 0.06, right? So, maybe let's transform the data, or let's do another different statistic, or okay. I have a slide later on that sort of describes some of these things. Or let's just add more animals, right? Those are examples of where the probability of a really just a false positive result increases the more fiddling you do to make an experiment work. Insufficient statistical power is a big one. Partial reporting is a big one, because if you have done multiple measures, right, and you decide, okay, well, I did 20 measures on this group of people or animals or cells, and one actually gives 0.05, but the rest don't. If you only report the one, then nobody knows that you've actually done 20 comparisons, right? So what is the probability of getting one significant result at p less than 0.05 out of 20 experiments? Normally I ask somebody that question. The answer is that there's a very high probability. That's what 0.05 means. You're going to get a false positive result 5% of the time, 1 out of 20. So if you don't report that you've actually done 20 analyses, then that is, again, one of these things that pushes toward a false positive result. Lack of self-replication. Do the experiment twice if you can. It's just the best way to do it. Really fundamental. Lack of transparency. Explain the data, explain the methods that you use to generate those data, and do it, really as fully as you can. And the other thing that really contributes to the false positivity is lack of is publication bias. If you do an experiment and your results are not statistically significant, a lot of times, and in the past, almost always, you couldn't publish those results, right? Many journals these days are actually now not only allowing, but encouraging the publication of negative results, because you did the experiment, you worked hard, the ideas were good, but okay, the experiment didn't work, fine. But if nobody knows that experiment didn't work, then the field has wasted a ton of money. So there's actually a very, I think, important and significant move toward publishing negative data, which contributes to the growth of knowledge. I'm almost at an hour, and I'm not going to go through necessarily all of the slides. I'm going to go through just the next few to show you that I've sort of gone through. I've talked about most of the things verbally. These are things that are just I've already mentioned, but the person who really identified these as 6 red flags is Begley. You can read that paper if you want. There's some things on what is being done. If you're interested, what NINDS has done, what the NIH has done, things that are being done to emphasize the review criteria in grants relating to scientific rigor. NIH has developed training modules on scientific rigor. So for those of you who are interested or who want to learn more, or more likely may need to learn more, check out NIH's sites. And here's one of the big ones that we actually published back in 2012. This is the first paper on really about what can be done for scientific rigor. And again, the big thing was transparency, reporting everything. This is sort of back to Joshua's question, how much detail? Lots of detail. Okay. All right. So here I've actually just got a bunch of things that just are sort of reminders of what I've talked about. I'm not going to go through these. Some other things. I do want to mention bias. When we use the word bias, sort of the first thing we think about is that we are biased in our thinking, right? That's not what scientific bias is. Bias is, I love this definition by Ransohoff. It's unintentional and unconscious. It's broadly defined and actually, happens to all of us, is a systematic error we make because we haven't formalized things that are important to eliminate bias. So what do I mean by that? There are things that need to be done that reduce bias. So we use the word, all right, random assignment to groups, right? That's something that's critical for minimizing bias. What does that mean? Well, random, I read so many papers where somebody says I randomly assigned animals to groups. And if I'm a reviewer, I always write back in my review, what do you mean by random? How did you do it? Right. And most of the time, people really don't do random assignment. You'll get 4 animals in a cage. You'll reach in, you pick one animal out, and that's maybe group one. You reach in and put the next animal out. Well, those of you who do animal research will know that if you reach into a cage of 5 rats, there's going to be one who's nice and sitting there saying, hi, take me. And the other one's over in the corner saying, you touch me, I'm going to bite you, right? You're going to naturally take the one that says, hi, take me. But that isn't random, right? You're not planning to segregate on that basis, but that's the place where things happen in a non-random way. So, for example, what I mean by systematic randomization is, for example, the day before we do an experiment, we number the animals, and then we use a random number generator to assign animals to groups. Okay, that's random. You can do the same kind of thing in a human subjects experiment where you're actually really truly assigning random. And you need to transparently report how you randomized in the paper that you're publishing. This Ransohoff paper is a really beautiful paper. Blinding is another example. There are all kinds of ways that you think you're blind, but you're really not. But there are formal techniques that are available for minimizing sampling bias. Systematic random sampling is another. These are things, for example, if any of you are doing tissue culture experiments or cell culture experiments, you have a field of cells, right? You've done a manipulation, you've treated them with a drug. You're going to now ask, how does it change their size or shape? How do you sample those? Well, most people in the past would have just gone in and sort of picked a group of cells. They say that's random, but it's not, because your brain, your eye, cannot avoid selecting on the basis of something. Most often it's because, well, the cell looks healthy, so I sampled that one. If you want to sample randomly a set of cells in a culture dish, what you need to do is actually plan the sampling in a systematic way so that it's random. And the way we do it is just put a grid on, you take the cells in X grid or cells that are at the crosshair or whatever. Those are the ways that you can define it. You can define the way that it's randomized, and it is in fact random. Need to, again, transparently report that. Okay, I've talked about that. These are called design-based strategies for randomization and blinding. I won't spend any more time on that, but I do have it there. I've talked about lack of contemporaneous controls. I won't go any more into that. P-hacking, if you want to read this amusing little article from Tom Insel when he was director of NIMH, it's kind of fun. Just a definition of p-hacking. Some examples. Okay, I've talked about all of these. I just want to do a couple of more things just to mention. How do you actually design an experiment? Is it, I have a hypothesis and I'm going to test it? Most of the time, that's probably what people do. hypothesis testing is considered to be the sine qua non of experimental design by NIH. But there's a problem here because you can do all the work and your hypothesis turns out not to be supported, and in many cases, where are you then? The answer is often, no, I don't know. That's not very good for NIH grants. The other way of doing it is sequential testing of alternative hypotheses. There's very rarely hypotheses that are, sort of the only possible explanation. The one that I prefer, by the way, and these are just delightful articles, is called Strong Inference, where you try to do a systematic test of multiple hypotheses. And the paper on this actually came out in the 60s and pertained to molecular biology. But I make my students reread it every year. It's just a wonderful way to think about science. And you can click that link if you want. Okay, talked about that. Sex, briefly. NIH realized that all the experiments that were being done with animals often, I shouldn't say all, many did not take the sex of the animal into account. And we came to realize, certainly in spinal cord injury, that there were huge sex differences. NIH now requires a section on that considers sex and other biological variables. And those of you who write NIH grants, you will run into that. My advice is have a section with a heading that says consideration of sex and other biological variables. It does not mean you need to do all your experiments with both sexes. We happen to have a couple of people here at UCI who are really leaders in this field and the emphasis, and Larry Cahill is one of them. So just if you have issues regarding inclusion of sex in your proposals, Larry would be someone to talk to. And this paper, by the way, is one to read. Okay, I am coming to the end. I want to end with journals. And again, about a decade ago, the journals really came together and said, okay, we get it. We were trying to save money, save paper, not have long method sections. Now we're going to do something about it. And the journals have really, the major journals have come together and really have pretty well-defined rules on what needs to be included for transparency of methods. This article was by Marcia McNutt, who was editor-in-chief of Science at the time, but it's true of many other journals. These are some of the links that you might find helpful for neuroscience studies. I was PI on a grant for the Society for Neuroscience that developed a number of training modules in scientific rigor. Those can be found on the Society for Neuroscience website, although I think you have to be a member, sorry. But there are other resources for creating a paper that really is maximally rigorous. I'll just use the word estimation statistics. Instead of you have a statistically significant difference, you report both that, but also the confidence intervals. It's really actually a good way to do things. Just to say, how big is this effect, right? And I'm going quickly here because I know we're running close to the end of the hour here. I mentioned this cell journals. These are the STAR methods that are required. And again, if those of you who are publishing in cell journals, you're going to have to do this. Structured, transparent, accessible reporting. And they really want everything. And I think this is a fabulous way to actually maximize the probability of having all the information that you actually need to try to replicate a study. A couple of others, scientific rigor publications and informational sources. And this is the last slide, I believe, that just sort of summarizes all the things that different journals have done to try to establish things that are promoting scientific rigor and even more accountability. So replication studies, negative results. Again, some journals specifically ask or allow publication. More options than ever before. Author contribution statements. This is becoming more and more important. When you publish a paper and you have 10 authors on it, who did what? Who's really responsible for this analysis? Who's the one who's done that? A lot of the journals are actually requiring that. And again, this is useful not only for scientific rigor, but it's useful for, those of you who are looking for jobs, right? What role did you play in that Nature or Neuron paper or science paper or whatever? When there are 10 authors and you're in the middle, it's hard to tell unless they're author contribution. There are these other things, the Kasrai contribution roles taxonomy, ORCID. I would encourage all of you to get an ORCID number if you haven't already. It's what you can use forever to identify yourself. If you change your name for whatever reason during your scientific career, your ORCID number remains the same. And then finally, there are a lot of things going on now post-publication. These are community-led accountability things. Some of them are kind of, I don't know. I talked about the so-called sleuths who are going around just trying to find things, but there are other quite, I would say, legitimate things that are being done to have discussions. If papers are, if there's questions about papers, talk about it. Post-publication comments, community vigilant, crowdsourcing. All these things are useful because at the end of the day, what's most important in my mind is getting it right. And if you have to take a hit for something that you published that was wrong, that's not a problem as long as you're the one that's leading the effort to try to get it right, I think. So with that, I'm going to end and happy to answer any questions, and hope that you guys enjoy the rest of your brown bag lunch here.
So I want to thank you, and I just want to highlight to everybody who's on the call today and who will be looking at this is that, you've been at the forefront going way back, as you said, to the early 2000s, and there was a really key paper that you were a co-author on. Landis was the lead author on that. That appeared in Nature, and that really awakened a lot of the journals within the American Physiological Society. That Landis article that you co-authored was cited as a major force in terms of moving the various journals towards enhancing rigor and reproducibility. So from my perspective, we're fortunate to have somebody with your gravitas in this area. And, so kudos to you for really leading this charge for over the last almost 20 plus years now.
Thank you, Vince. My mother would love to hear that I had gravitas. That's the last thing she would expect. Okay. By the way, and if any of you just have questions, I'd be happy to, send me an email. Or if, this was an introduction. Most of you are going to kind of say, okay, fine. And you're going to go off and start doing your research. And then probably about a year and a half down the road, you're going to say, maybe that's the point at which you'll hopefully come back to some of this. But I really would emphasize that it starts at the design stage and is critical during the execution stage. So at least think about it now. But if any of you have just questions or whatever, I'd be happy to answer them to the extent that I can.
The other thing I have to comment about, which cracked me up when you're talking about, but is definitely true, is that for those of us who've worked with rats and mice, we do know that there are ornery rats, and you tend to shy away from picking those animals. So your comment there was pretty comical, I thought, because I've definitely experienced that firsthand.
Right. Yeah, sometimes you just put those guys away and just say, I'll deal with that one tomorrow.
Yeah.
Mm.
Really quick question, Stuart, about you mentioned at the beginning of your presentation that that the PIs and the senior PIs may be stuck in their ways, and it'll be maybe the up and coming scientists, the grad students, and the postdocs that may drive a lot of these changes that you're mentioning here. And I was curious, in your opinion, what may be a good approach for someone to take if they're talking with their PI or their senior PI and they're trying to say, I've heard about doing this thing a different way, and I think it could be beneficial. Like, what's the best way? I know it may be tricky, because people may have different things that they gravitate toward. But maybe if you could just speak for yourself and what you would respond to if you had a early scientist coming to you and approaching you and wanting to suggest something to do differently that you may have been doing a certain way for years, but they're suggesting something different.
That's a great question. um, I would say I would hope that I would be receptive. I would hope that everybody would be receptive. The fact of the matter is that's probably not going to be the case. And it's usual when you talk to your PI about anything like that, prepare yourself. I think one of the ways that I would suggest doing it is to really start by the end. I served on the governing board of California Institute for Regeneration for 17 years. I actually am the longest serving member of that. That's the stem cell board. And one of the things that I learned from the people who do clinical trials is think about the clinical trial at the beginning. In other words, think about the end. And it really is the same for science. When you're doing a set of studies, think about where you want to publish it, right? It might be Science, it might be Nature, it might be, well, I'm not going to get there, but I want to go to this really good journal. And so to answer your question, I would start with where you think you're going to want to publish it and look at their requirements. What do they expect? And some journals will just lay it out in really extensive detail. And then you have something that you can use to go to your PI and say, look, this is the journal where I think this is going to go, I hope. These are the requirements that journal has. I'd like to do the experiment in the beginning the way that journal requires. Then you kind of dodge all the personality things about whether what the PI has been doing for the last 20 years is actually the right way to do it. That's the best advice I can. But I'm sorry, you're probably going to run into problems no matter what. I hate to say it.
Thank you. That's good advice. I like what you said about thinking about where you want your work to end up going at the outset. Typically, that discussion is had after it's done.
Exactly.
So I think it's good advice to think about that at the beginning.
Yeah. Thanks. Other questions?
Well, if there's no other questions, Oz, thank you very much. You're always very giving with your time, and we really appreciate your insights on this and all other topics.
Thank you.
So with that, we'll bring this to a close, and we look forward to seeing you in our next brown bag. Thank you.
Okay. Thank you very much.
Thanks, everybody.